The fifth one, this is Pitot tube. Okay, this device is used to measure the speed of an airflow. Now this is built like now take a normal ballpoint pen. Now assume that okay, pen is like this, right? There is the tube with the ink. So this is the tube with the ink, and there is a covering to the pen like this. Okay, this is the end of the pen. Now assume there are no ink, and the tip also, there is no tip. Here. So this is a opening. And assume that here there is a hole, and the tube is extended somewhere here, and it is again connected to this larger tube like this. Okay, now I'm going to draw this here. So what we have is we have a larger tube, and inside that we have a smaller tube. Okay, the smaller one comes it turns like this, and again comes and connect to this. Okay, this is the device. Apart from that, there are some openings to the atmosphere like this in the larger tube. Okay, there are some openings to the atmosphere. That means atmosphere is in this the atmospheric pressure is in this tube also. But in this section there is a fluid. It doesn't have to be water or something like that. It can be any fluid put inside this section. This acts as a manometer. That means manometer is used to measure pressure difference. So there will be a pressure difference after some time now. Okay, now what happens is, consider there is a airflow. So let's take three streamlines. This streamline will go like this, and it will go like this. Okay, like this. This one also, it will go in this direction. This streamline will enter the tube, and here it will come to rest. Here the streamline will come to rest. Let's take 2 points, this as x, this as x point. Here let's take the pressure as P1 and velocity as V, and let's take here the pressure as P2 and velocity is here. Now U is 0. Velocity is 0. There is no velocity to that point. Why? It has already come to a stop here. There is no velocity. Okay, so here velocity is high, pressure is low. Here velocity is low, so therefore pressure is high. Here pressure is high. Due to this high pressure, it will push this liquid down. And from this side it will rise up. It will rise up. So now we'll get a height difference like this. Let's take the height difference as simple h. From this height difference we can actually measure the pressure difference. Pressure at this point and pressure at this point, we can take the pressure difference. Let's mark this point as A, and a point just below the liquid surface as B. Now you should remember, this is what we did in fluid statics. We found out, we equaled the pressures inside the same level, inside the same liquid in same level, and we took the pressure difference from that, equaling the pressures. We'll do that in a minute. So this is the diagram. Now let's name this tube, this larger tube, as P. Don't confuse with the pressure terms are written using P1 and P2. This is the P tube, and this smaller tube is the Q tube. Okay, P tube and Q tube. Those are the terms used in the note, therefore I can't change them change them now. It is better if this is in some other letter other than P. If not, sometimes you might get confused thinking that this has a pressure. This is not a pressure. This is the name of this tube, P tube, and this is Q tube. Okay. Let's equal the pressures at these 2 points. This is already typed, but I'm doing it anyway. PA equal PB, pressure at A equal pressure at B. Pressure at A can be written as this pressure plus H rho G. For this density, let's take sigma, density of the liquid, because we are taking density of air as rho, so we have to take another symbol for the density of this liquid. So pressure at A equal this pressure. What is this pressure? This is open to this place. Okay, this place and this place is kind of same. Why? Streamlines are almost unaffected at this place and at this place. So if the pressure is P1 here, then here also pressure is P1. Here also pressure is P1. Actually, I can write pressure at this place as P1. P1 and velocity as V. Velocity and pressures are unaffected. Here also velocity, pressure is P1 and velocity is V. Those are unaffected. So pressure at A point can be written as this top pressure, that is P1 plus H sigma G. PB is equal to what? PB is equal to this P2. PB is a place just below the surface of the liquid, so it is P2. Okay. Now I can take the pressure difference P2 minus P1, P2 minus P1, P2 minus P1. This is already typed in the note, equal H sigma G. Now let's apply the Bernoulli's equation to the places. Didn't we name this place? This should be Y. This is X place and this is Y place. I'm applying Bernoulli's equation for X and Y places. It is already typed for points X and Y in the streamline. Applying Bernoulli's equation. If I apply Bernoulli's equation, I can write P1 plus half rho V squared equals, there is no rho GH term because these are in the same level. Equal, here pressure is P2 and we don't have anything else. The velocity is 0. so don't need to write the kinetic energy term, velocity is 0. So here I get P2 minus P1 equals to half rho v squared. So this is P2 minus P1 and this is P2 minus P1. These are we can write this as the first equation and this as the second equation. It is not marked in the note, so you can name these equations 1 and 2, and I can equal the two equations 1 equal 2. So I get first I'll write this part, rho half rho v squared equal h sigma g. So what I have to find is velocity. Velocity is equal to h sigma g divided by rho and square root. So this is the velocity of the airflow. Sigma is the density of the liquid in the manometer and rho is the density of air. When I am applying the equation, Bernoulli's equation, P1 plus half rho v squared, half rho means then density of the fluid, the density of the fluid flowing at that place, that means air, density of air. Right. As I said in the beginning, this device is used to measure the speed of airflow. So if we know the density of air, density of this manometer liquid, and if we measure the height difference, then we can substitute the values and calculate the velocity of the airflow. Right. You only have to draw the diagram in the given space. So after the equations, there are some important points here. To achieve a clear difference in liquid levels, the density of the manometer liquid should be somewhat a lower value. If not, there won't be a significant difference in the liquid levels. If we take a high dense liquid for the manometer liquid, like suppose we took mercury for some reason. Mercury is a highly dense liquid. So if mercury is used to denote this pressure difference, then it will be very small height because density is very high. Therefore, H will be a small value. So we can't measure it and we can't see it clearly. So we should use a lower density liquid as the manometer liquid. And the other thing is this method cannot be used to measure the speed of a liquid because it will lead to some issues like the liquid will, if we use this to measure the speed of a liquid, the liquid will come and it will hit this manometer liquid and this manometer liquid will be displaced from this place. So we can't use this device to measure the speed of a liquid flow. Okay.